AI accelerating the coverage closure using intelligence stimulus generation. The abstract, as the number of intellectual property covers in the modern SoC designs continues to grow, coupled with the increasing trend of the multi-chip designs, the complexity of the bus metric has significantly evolved. So interconnection implemented across the various layers to meet the timing requirements and support many initiators target ports with mixed protocol. Consequently, functional coverage has become the critical aspect of SoC verification, particularly for ensuring the comprehensive validation of interconnection and their data paths. However, to achieve the functional coverage for such complex SoCs, which often involves an enormous number of beans, sometimes nearing a million, presents several challenges. For instance, on SoC with 150 initiators and 500 targets must cover the cross product of the parameters like initiator, target, size, length, burst, and others as applicable. This complexity can result in more than half a million beans, complicating the management, analysis, and reporting, necessitating the substantial computational, the resource, and advanced tools. To achieve full advantage for this means in a complex SoC, thousands of iteration intensive manual efforts are required. Moreover, after a certain point, when coverage saturation is reached, randomized input stimulus fails to provide a significant incremental coverage in successive iteration. This occurs because the current randomization engine repeatedly hits the same bins, leading to the diminishing returns in the coverage progress. Consequently, this prolongs verification closure timelines and can adversely impact time to market. To address this issue, adopting the artificial intelligence, AI, and machine learning ML technologies and the design verification DV environment is crucial. This paper proposes leveraging the AI ML-based technology using the input bias feature of the Cadence Xcelium SimAI tool to accelerate functional coverage convergence while preserving the randomness of the stimulus. In the proposed approach, an input bias file is derived based on each initiator constraint and each corresponding accessible target. This file is provided as input to the AI tool, which utilizes in-monitor coverage. Based on the feedback, the AI tool determines which input constraint should be given higher weightage, ensuring that a new cover groups and bins are targeted in subsequent iteration instead of repeating the same bins. So this approach not only prevents coverage saturation, but also enables faster coverage achievement in fewer iterations. In additionally, it facilitated the coverage of cross-bins identification of corner case in scenarios at an early stage, significantly enhancing the efficiency and effectiveness of the SoC verification. Chapter 1 Introduction. In modern SoC design verification, achieving the comprehensive functional coverage efficiently is crucial to gaining confidence in the overall SoC verification. Functional coverage, including cover groups and cover bins, plays a critical role in ensuring that various routes and scenarios within the interconnect are thoroughly verified. To handle today's complexity SoCs, more sophisticated and structured interconnection designs are employed to ensure proper timing, closure, and functional correctness. Specifically, in data route verification, it's essential to verify that communication between different IP blocks and subsystems function as expected under all conditions. The sheer number of the corner bins and coverage groups is growing exponential, leading to a significant challenge in achieving comprehensive verification. Furthermore, with coherent the interconnect, it is necessary that initiators, coherent or non-coherent, and target DRAM, memory, etc., and etc. support various protocol configurations. In such scenarios, cover points that involve crosses of the parameters such as source, destination, transition type, data size, and request type, and length region in a massive number of cover bins that must be covered within a limited time frame. Covering such an extensive number of coverage groups becomes a bottleneck, making it impractical to cover all corner cases due to the constraint on time and resources. Additionally, achieving coverage closure requires running many test cases. With an increasing number of cover bins to hit, simulation times become prohibitively long, especially for large and complex SoCs. Moreover, large SoC designs demand significant memory and computational power to store and track coverage information across all cover groups and bins. Leading to resource constraint in simulation farms, operating under constrained environment, limited resource availability makes exhaustively simulation for large design infeasible, resulting in performance issues and extended verification timeline. Some corner cases may remain unreached during regular simulation runs, and either due to the rarity of the conditions required to trigger them, or the becomes the redundant coverage bins consume variable simulation time. To address these challenges, an approach is required to achieve faster coverage closure with the verification timeline. The proposed method accelerates functional coverage by leveraging the advanced technology and methodologies such as artificial intelligence (AI) and machine learning (ML). This paper specifically utilizes the input bias feature of the Cadence Xcelium SimAI tool. This method effectively analyzes a large set of coverage bins over 600,000 and biases input constraints based on feedback, thereby improving both speed and accuracy. The proposed solution has been applied to real designs, resulting in a 30% reduction in overall bus verification closure time. This method uses iterative evaluation to maximize the coverage and achieve faster closure with fewer regression runs compared to the traditional approach. Figure 1. Multiple chips connected to via UCIe in a typical. On each iteration, the AI engine evaluates and identifies coverage holes. The machine learning model is then updated with information about its performance. The basic flow is to run random regression with coverage and randomization data. When coverage becomes largely saturated and is growing slowly, then use the AI tool to target coverage holes more efficiently. The AI tool can be trained at any phase of regression using the previous run as the base regression session. After training, the tool iteratively repeats simulation runs to target coverage holes until coverage is fully closed. The key goal of the AI tool is not just to regain coverage, but to increase the probability of hitting coverage holes. During the coverage closure phase, The AI tool performs full random runs to stress the design in various ways while targeting coverage whole. Chapter 2: SoC Cover Group Structure. For complex SoCs, it's crucial to ensure that a combination of source IP, destination IP, transaction types, read and write, data sizes, lengths, and etc. are fully exercised. In such cases, cross-coverage tracks whether all combinations of these variables are covered. This is vital for testing SoCs with various subsystems connected through the multiple levels of interconnect supporting different protocols. However, as the number of the cross coverage beings increasing, the time combination grow exponentially, leading to challenges such as longer simulation times and potential coverage gaps. Despite these challenges, cross coverage is essential for the comprehensive verification of complex SoC designs. The Figure 2 shows some of the possible combination of cover groups for an AXI initiator accessing multiple targets with a constraint defined for each target. To create such extensive coverage groups for a complete SoC, a Perl script is used based on input files containing initiator constraint, target address space, and initiator target reachability. The script generates cover groups for each initiator targeting or the path accessible target. Additionally, the script generates monitor connection files, simplifying the integration into any UVM-based framework environment. The script is also capable of ignoring illegal beans or invalid beans during the process. And the figure 3 illustrated this workflow. Workflow. And Figure 2 cover group formation of for AXI initiator in an interconnect and corresponding similar cover group definition. Figure 3, script utilizing input files and generate plug-and-play coverage files. Table 1, coverage beans analysis for various SoCs. The script maintains an initiator database and target database is simplified generation of cover groups for each initiator, as shown in Figure 4 and Figure 5, respectively. This database contains various fields that are updated using the information provided in input files, such as initiators constraints, and reachability information, and target address range. For a particular initiator database, the field can be added or modified as required. For example, in the case of the APB protocol, the target list is divided into active APB target, slave underscore list underscore APB underscore A, and passive APB target, slave list APB underscore P. This distinction is helpful while creating a cover group for active agent. An initiator can have the possible direction of the read and write, whereas the passive target's possible direction is limited to read. This ensures the unnecessary write operation to the passive target, which can potentially alter the behavior of the RTR, are avoided. Maintaining such a list also helps to prevent the generation of illegal crosses. The coverage output of the coverage file output from the script will have a coverage group definition for each of the initiator as given below. Depending on the project, valid cover groups identified are listed in Figure 2. It's important to note that the number of cover bins increased to 3 to 4 times when the same die is implemented in a multi-die step, setup further complicating coverage closure. Chapter 3. AI Setup in Simulation. The AI framework uses randomized and coverage data from the design and test bench to create a machine learning model that accelerates regression performance. This model learned from an iterative regression sessions and generates optimized regression based on predefined criteria such as stressing specific design instances, minimizing directed test, or maximizing regression throughput using random tests without committing seeds. The complete flow involves a series of steps that uses existing regression or simulation runs as input, generate learning models, and synthesizes an optimized version. Using this simplified flow, you can applying machine learning and synthesized regression and learn the synthesized regression. A. Machine learning. To implement the regression for machine learning, the simulator uses appropriate switches to analyze all the random variables during regression runs. This step creates a base regression run that serves as input for the AI tool to analysis and build learning models. Any regression can be used as a base regression run regardless of coverage level. At the end of each base regression run, the AI tool generates several files obtaining the configuration and path information, coverage bit vectors, and randomized data necessary for regression synthesis. B. Synthesizing regression. During the synthesizer phase, the AI tool enables an iterative learning flow framework, allowing it to repeatedly learn from the original input regression and other saved data. Within this framework, users can explicitly define use cases and convergence policies. For example, users can enable coverage maximization, directing the AI tool to synthesize regression to target and cover bins from the original regression. Learning a synthesized regression helps generate scenarios targeting corner cases or other critical areas, improving coverage of error conditions. It can also be used for bug hunting runs, filling a CPU budget, or targeting challenging bins, including cross-coverage bins, requiring the multiple runs. Finally, the AI tool generates synthesized regression based on the base regression, which may include small, optimal, or exploratory regression runs. It saves datasets, running models, synthesized regression, and reports in a directory, which are used in subsequent iteration of the learning. C. Random synthesized regression. The synthesized run from the early setup is then utilized with the default learning database to cover random variables across all possible cover group information to refine convergence at one-time input bias file is provided containing the cross-coverage definition and user-specified random variables. This file enables AI tools to analyze regression outcomes in line with the input bias structure. With each new regression run, the learning matrix is updated, allowing the AI tool to evaluate the impact of control knobs. The input bias file specified valid beans for each initiator and accessible target, avoiding invalid beans that could degrade performance by wasting time attempting to close them. This input bias file is also generated using the same Perl script as discussed above. Below is an example of a file content that coverage aware. 4. Features. The use of AI ML tools for functional coverage offers the following features. Automatic constraint learning. The AI tool generates a learning model by analyzing all random variables in each base and main regression set. This model includes a constraint variable information for all possible inputs stimulating the initiator in the design. The AI tool updates the learning model with each regression run, ensuring it adapts to the latest constraint scenarios. B. Intelligent feedback mechanism and coverage gap detection. The AI tool automatically analyzes, synthesizes regression runs and compares them to the learning model from the previous run to identify the cover group patterns with a zero hit ratio. Using coverage gap information, the AI tool recognizes uncover cover groups and determines the convergence strategy for subsequent regression runs. Automatic coverage gap detection is especially critical for managing the design with hundreds of thousands of beans. C. Optimized stimulus generation. The input bias constraint file generated from the cover group model provided the AI tool with the visibility into the relationship between the constraint and associated cover groups. The AI tool analyzes the information its biases to the input stimulus to utilize specific random variables effectively. Intelligence, the test benches, test stimulus. Based on the input bias file, the AI tool eliminates redundant tests that do not contribute to the additional coverage. Subsequent runs are more targeted at uncovered beans while maintaining the randomization, ensuring the efficient resource utilization. So the chapter 5 is advantages. The implementation of AI ML-based coverage closure streamlined functional coverage achievement offer the following benefits. A. Dynamic stimulus adjustment. The proposed approach allows input bias stimulus to dynamically adjust it at any stage of the coverage and activity based on the base regression set. This feature enables seamless utilization of both generic test vectors and AI synthesized test vectors, making the approach robust and adaptable. B. Easy implementation. Integrating AI ML into regression setup is one-time effort performed at the start. This setup is easily portable to other projects with minimal changes. Furthermore, the automated generation of the input bias file makes independent of the number of beans or the scale of the design, allowing the effortless information implementation in any SoC. C. Scalable approach. This method is highly scalable and independent of the design architecture. It's further future-ready and can be implemented in multi-architecture with minimal additional effort. The AI tools demonstration superior performance and a larger design and offering the high coverage efficiency. D. Efficient resource utilization. By optimizing test vectors and synthesized regressions, the AI tools significantly reduce the number of iterations required to achieve the coverage closure. This compressed regression approach to maximize the coverage while minimizing the simulation time and computer resources and memory requirements. E. Reduce time to market. AI ML-based coverage-driven enables early analysis of the corner case cover groups and early detection of the design bug, significantly accelerating the time to market for products. Chapter 6 is result. When applied to a real design, the following results were achieved. A typical mobile platform fabric with approximately 100 initiators and 380 targets, targeting the 600,000 beans. Achieve the saturation at 98%. After saturation, 8,400 simulation hours of regression runs were required to achieve 100% coverage. However, using the proposed methodology, the time to achieve the 100% coverage was reduced to 3.8 kilo simulation hours. It was observed that the AI tools deliver better result when trained early in the regression phase. For a typical hard-to-hit cover group, achieving the AI with the input bias solution showed a significant improvement. Initiator is 100, target 380, target coverage being the 300,000 more than 300,000. Original regression, more than 8,400 hours, 98% coverage. Input bias, 380 hours, 100% coverage. Table 2, improved for coverage to 100% using AI tool. Figure 6, AI generated coverage versus number coverage after applying the ML at 88% and 46% respectively. Figure 7 is AI generated coverage versus number coverage applied to the same regression with different base regression. Figure 7 shows a graph when applying the AI to regression at an early stage of the regression. It's evident that a higher gain are observed when AI is employed earlier. Group initiator 38, less than 38, 380. The target coverage beans 9,250. Original regression greater than 8,700 hours, 85% coverage. Input bias 380 hours, 8 hours, and 100% coverage. Conclusion. The AI ML approach has been implemented in various complex SoCs with the coverage beans ranging from 0.8 billion to 1 billion. Under normal randomization stimulus, coverage typically saturates in the final stage and requiring more iteration to complete. In contrast, the input bias approaching the dynamically adjusted stimuli based on non-hit beans after each iteration, ensuring constant increase in coverage. The dynamic adjustment prevents saturation and achievement 100% coverage closure in and lasted 30% last time. By leveraging AI methodologies, this approach maximizes coverage with a reduced regression set, irrespective of the number of the beans in a design. Okay. Today, I read this paper, the AI accelerated coverage closure using intelligent stimulus generation. Thank you for your time. See you next time.